Okay, in this video, we're going to talk about physically based rendering, which is an important concept to understand nowadays if you are in the animation, gaming, and visual effects field. So, defining physically based rendering is a little tricky, but the general concept is that with modern advancements in rendering and shading, we are more accurately or closely simulating the way light moves throughout a space and how it interacts with surfaces as it does in the real world. So, it's more physically correct. We're using values and concepts that are, referencing real life. Previously, we would still be trying to reference the way light interacts with surfaces in real life, but it was much more hacky and using a lot of tricks to simulate this. This is, of course, due to the technical requirements and limitations at the time, but it was not really a concept, or the way of approaching it wasn't technically correct according to how light behaves in the real world. PBR surfaces often rely on a simplified model of what's called the bidirectional reflectance distribution function, or BRDF. It's a fancy term, but generally we're not going to be diving into it here, but you'll see that term pop up a lot. But this is essentially the model or the function that is approximating most of our light interactions for materials using just a handful of parameters. If you have access to these slides, I also have these links for further reading into this concept. So to start, we need to back up a little bit and do a summary of how light works. Light, as you may know from physics class, is electromagnetic radiation that, for these purposes, we're thinking of as waves. Light is emitted from sources like the sun, or incandescent light bulb, or my monitor, and all other objects that we see in the world are just reflecting light back to us. They're not creating light. So color of light is based on the wavelength of light, where red has the longest wavelength and violet has the shortest wavelength. If you look at the electromagnetic spectrum, that goes from radio waves all the way down to gamma and cosmic rays. The visible spectrum of electromagnetic radiation is visible light. So that is what we see as visual information that stimulates our retina and creates images. So you can see on the left-hand side, the longer wavelengths is red, and then on the right-hand side, we have violet. And these are, of course, as you might expect, very, very small. So a single piece of thread in spider silk is essentially the size is 1 micron. And then the next step down in terms of size measurements is nanometers. And so we measure wavelengths of light in terms of nanometers. So you can see if a piece of human hair is 80 microns, then a wavelength of red light would be 700 nanometers. And you can see that the size relationship between this wavelength here compared to a single piece of human hair, that's like very, 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 very small. So we're talking on very small, almost molecule interacting sizes. Most light is made up of a combination of different wavelengths. So we have all these different wavelengths of light, and most light is made up of a combination of these. They're not just these single colors that you can choose from: red, green, blue, violet. They're usually a combination. And so we would call that polychromatic. White light would be every wavelength of visible light combined together to create a desaturated appearing light. And then a green light, so if you saw a light that was just green, would have just the green wavelengths of light. So it would be monochromatic. So again, as a repeat, we see the environment and the world around us as light that hits a surface, bounces off, and then reaches our eyes. The color of a surface or an object is based on the wavelengths that are absorbed by the object due to the chemical makeup of the surface. So some light is able to bounce off, but some light is actually absorbed by the material. The perceived color of the object is the wavelengths that are not absorbed and hits our eyes. So a green surface in this case, as you can see in the image on the right, would be all the different wavelengths of light that are coming from the light source being absorbed, so only green is allowed to come off and hit our eyes. So same thing with red apple. We see it as red because red is the wavelength of light that isn't absorbed and is reflected off and reaches our eyes. We have different terminology for the way light interacts with the surface in unique ways. So we have transmission. That's when light simply enters and travels through a surface or a material. Reflection is when light bounces off of the surface and doesn't actually go into that new medium or material. Refraction is when light enters that medium or material and changes direction. We're going to ignore diffraction for right now. It's not important. Absorption is when light as it enters a new medium or material, it changes into a different form of energy. So it's no longer light. Most of the time, turns into something like heat. And then scattering is when light enters the medium or material or hits a surface, and because of irregularities or molecules that are inside of that material, the light's going to start bouncing around, changing different directions. So light doesn't, compared to refraction, you might have a bunch of light rays that come in together and they change the angle together. So they stay together, but they're just moving in a new direction. That's refraction. Scattering is that group of light rays that come in and then each of them hit some kind of different surface and they bounce around and go somewhere else. And so for shading purposes and material purposes, it's really beneficial for us to break this down into two different general categories. So instead of thinking about all the different ways that light is interacting with the material and medium, we're going to kind of break it down to two simple categories. So we have light that comes in from our source from another direction, and then some portion of it is going to bounce off or reflect off of the surface. And then some portion of it, the rest of it, is essentially going to enter the surface and do other things. So we're going to kind of keep it into that kind of category. So reflection is describing the light that hits the surface, then bounces off, right? We're pretty familiar with what reflections look like and what they are. If we think of light as a ray that hits an object, it has both an incident ray, so that's the ray of the light coming in and hitting the surface, and a reflected ray. That's the direction and the ray of light that after it hits the surface and bounces off. Same light, it's just two different kinds of ways of thinking of it. So on a perfect mirror-like surface, these are going to have the exact same angle. The angle that it comes in is going to have an equal and opposite angle that it's going to reflect off of on a perfect surface. But of course, most surfaces are not perfect. So reflections on a material surface can either appear crisp and clear, like this ball on the right, or they can look rough and blurry, like this clay dirt ball on the left-hand side. And so the clarity or the sharpness of these reflections, like whether we can see an image or we can't see an image, is due to the microfaceting of the surface, which is the really, really small micro imperfections on that surface. So on a very small scale, that surface is very irregular and it's breaking up the light that's coming in, which means our reflections are some degree of sharpness or reflected or smooth. So a smooth surface has very little variation on it, which will reflect light rays coherently or together. So that light comes in together, leaves together. And so that creates a clear reflected image. But a rough surface, its microfaceting will be very irregular. So the light rays come in together, but then they leave at different angles because that surface is irregular and they're all kind of reflecting at slightly different angles, which means that our image is going to end up looking blurry. And so the greater these differences are, whether they're much larger angle differences or there's just more differences in imperfections on the surface, is going to cause blurrier reflections. So, on a surface that's a little bit more smooth, it's going to have a more coherent and easy to understand image. And then the more imperfect it is, the rougher that image is going to look. Some terminology you'll see is glossy, mirror, and matte. We're going to ignore that term for a second. So mirror would be a theoretical perfect reflection. So there is no imperfections. It's just a perfect reflection off, which means that you would see, just like a mirror, a perfect image. A glossy surface is going to be sort of perfect. It's going to have a pretty coherent image. This one's actually not a great example, but the light isn't scattering all kinds of different directions, but it's starting to kind of separate and be a little blurry. And then matte would be almost completely, all the light is scattering uniformly in all directions, which leads to a very blurry reflections where you can almost not even notice that it has reflections on the surface. And here we can see some material examples and their relative value, whether they are glossy, right, or they are rough or diffuse or matte. So the rougher materials are going to be materials like stone, plaster, dirt. And then as we go further and further up, going into wood and then plastic and then metals and then an actual material, we're generally going to get clearer and sharper images in our reflections, right? So look at those reflections. We're noticing that they're getting a little bit more easier to see and more prominent until, when you have a perfect mirror-like surfaces, those images are almost perfect as they are reflected off the surface. So transitioning to the next material interaction besides reflection, we kind of have to cover, I'm just going to mention this term right now because it can be a little confusing, because as with everything else, some terms mean different things depending on what you're talking about. So you'll hear the word, like right here, diffuse, right? And so there are reflections that are diffuse. Generally what that means is that light does not follow the angle that it comes in at, right? It actually scatters in a lot of directions, right? So here with a mirror-like surface, the light leaves at more or less the same angle it came at, but in a diffuse reflection, it doesn't follow that incoming direction. It just goes in a lot of different directions. But for shading and physically based rendering purposes, we're using a different term, or we're using diffuse to describe something else, which is that light that doesn't reflect on the surface, but actually goes underneath the surface or enters the surface, where it scatters around, does all kinds of complex things, and then comes back out. So diffuse is how we're describing the light that travels underneath the surface. Any light that isn't reflected is going to enter the surface. So beneath the surface, it will interact with the material in a number of ways, including scattering, refracting, and absorbing. So scattering is pretty easy to understand. It's essentially when light doesn't travel in a single direction, but hits an obstacle, like a molecule, and is redirected in different directions. Refraction is how light bends when it enters or exits a material. The light changes the direction but doesn't scatter. So it's a little, like I mentioned earlier, different than scattering and refraction. They sound similar, but they're actually a bit different. And absorption is when a wavelength of light is converted to another form of energy, like heat. When a light wavelength, like red wavelength of light, is absorbed, it changes the color of the light that's still traveling. So if light is like white light enters a surface and then the material is absorbing all the red wavelengths of light, then you're changing that color of the light that is still going through. So you're left with that white light minus the red wavelength of light. The light that enters the surface can either change very little, like if you have light going through glass, or it can have very complex interactions, with, like bending as it enters the material, scattering around, and changing its color as it's partially absorbed. What's important to understand is most of the diffuse light is eventually reflected back out of the surface to reach our eyes, right? So we're still seeing that light that enters the surface, so that means it has to come back out of the surface. And we'll see on the right-hand side, this is a picture of a girl, right? And this is just a normal picture. And through a photographic technique, you can see they're removing the specular reflection. So that specular light, which are all those shiny bits, are now removed, and that's all that other light that's entering the surface. So here's another example. On the left-hand side, a normal picture of a guy's skin. On the right-hand side, they're removing all the reflection components. So we're seeing all that light that actually enters the surface. So all incoming light, as a reminder, will either be reflected or diffused. The portion of light that isn't reflected, so the light that doesn't bounce off the surface, enters the surface. So transitioning to terms that we're going to see in shading materials, we're going to define that reflection and light entering the surface as specular and diffuse. So specular is going to be that reflection, the light that bounces off the surface and doesn't go underneath. So usually, if it's not a metal, that's a very small amount of light, right? You can see on this girl's skin, most of what we're seeing is not the light reflected off, it's the light that enters the surface. So that's the specular reflection. So on this apple on the right-hand side, that is that like kind of shiny highlight that you'll see on it. The roughness or sharpness of that is, again, based on the microfaceting, those irregularities of the surface on almost a microscopic level. And then diffuse is the rest of the light. That's the cell light that enters the surface and does all those complex interactions before coming back out. That's all this red stuff that we're seeing with all its different color variation. And unless it's a metal, this is the majority of light that hits the surface goes into the diffuse area, or the diffuse category. So this affects how we perceive the color of the object and also the light and shadow. So essentially, the shading of most non-metal objects is the diffuse lighting that we're seeing. That's what we think of as a red apple. Okay, so here's our apple. So most of the shading on it is diffuse, and then those highlights and those shiny bits are the specular reflection. That's the light that just bounces off the surface. And here's some examples showing the separation. So here we have a material inside a RenderMan. And on the right-hand side, we can see what the material looks like. And that material, broken into its components, or its basic components, is that diffuse light that describes the surface and color of the object. And then the specular, which is that light that bounces off, what we think of as the highlight. Again, going back to that picture of that girl, on the right-hand side, we see what a normal picture looks like. And then we see those two material interactions isolated. So that specular, again, is that light that is reflected off the surface, and diffuse is light that enters the surface. Here's another example with a boot. And these are using cross-polarization photographic techniques to separate these. So on the right-hand side, we see a normal boot photo. And then we have the diffuse, the light that enters the surface, and then the light that bounces off, separated out. So again, most materials in the real world, some portion of light reflects off the surface while the rest enters the surface. The light that enters the surface bounces around, changes color, and is either absorbed or reflected back out. So that's the diffuse, the light that enters the surface and does all that complex stuff and comes back out. And then the light that doesn't enter the surface and bounces off of the surface is the specular. So we have the diffuse and the specular. Diffuse, specular. Okay, so moving on, we also want to categorize, for simplicity's sake, our materials into these different categories. And you'll notice the word insulator, semiconductor, and conductor corresponds to the transmission of electricity, right? So different materials transmit or conduct electricity well or not well at all. So metals are usually good conductors, and then things like woods and rubbers and skin are very poor conductors of electricity. These actually are also affecting how light interacts with the surface. But for material interactions, we're not really worried about semiconductors, right? Because we're really thinking, because those are very uncommon materials that you're not going to see very often. Mostly we see dielectrics and metals. Dielectrics are essentially nonmetals. That's another term you'll hear is nonmetals and metals. So dielectrics are most materials we can think of, right? That's like clay, wood, stone, plastic, skin, grass, I don't know, lots of other things. And then metals are exactly as you'd think. That's like gold, copper, nickel, aluminum. And so that's in its own different category. So here's just another example. So again, going back to that concept of categorizing light as bouncing off the surface or entering the surface, with metals, light actually does not enter the surface. Or if it does enter the surface, it's fully absorbed and does not actually do interactions underneath and come back out. So metals actually block or fully absorb the light that would normally enter the surface. What this means is that metals, or pure metals, do not have a diffuse component. Instead, metals are seen mostly as specular or surface reflection. So when we see a metal and we think of a metal object and kind of how its form is described, it's almost all reflection and not actually light that enters the surface and scatters around. So metals also reflect a lot of light compared to most other materials. So 50 to 100% of light is reflected on a metal compared to a dielectric, which maybe reflects 2 to 16% of light. So metals, again, absorb diffuse reflections. So if I was looking at a material or a shader inside of my rendering program, I would want to disable or turn off the diffuse attribute. So in this case, in RenderMan, I'm setting my diffuse off or turning the color black so that it's only focusing on the specular reflections. The different metals will absorb different wavelengths or color of light more so than others, which means that it's actually changing the color of the reflections, the reflected light. So because of this, metals will have some tinted specular reflections as only some wavelengths of light are reflected off the surface. This gives each of our metals their characteristic color or look. So that's why gold appears kind of like a yellow color and a bronze will look sort of brown or orange. So here we can see the colors of the reflections or how the light is being tinted as it bounces off the surface for different types of common metals: gold, silver, aluminum, iron, copper. And so each of these metals has a unique tinting that they do to the reflections. So you can see that reflection isn't the actual image, the environment isn't yellow, but when it bounces off, it's turning yellow. Nonmetals, as we mentioned before, is essentially all other basic types of materials. And we call those dielectrics. So dielectrics are normal materials and they have that diffuse and specular light interaction. So unlike metals, which are highly reflective, dielectrics actually reflect only a small amount of light. The rest actually enters the surface and scatters around. So specular values for a nonmetal tends to fall between 2 to 8%, and more commonly around 2 to 4%. It can go up to something like 16% of light is actually bouncing off the surface, but that's pretty uncommon. That's like for gemstones and materials like diamonds. But most common materials are only going to reflect 2 to 4% of the light. So that leaves 96 to 98% of the light is actually light that just enters the surface. So that's why most of what we see of a dielectric object is the light that enters the surface. That's most of what describes the surface. So non-metals, aka dielectrics, are the lights that will have light scatter and travel beneath the surface. And so for nonmetals, we do want our diffuse light interactions. We want the light to go in and bounce around and scatter around. So we enable diffuse reflections. Also, notice how low or dark our specular reflections is, because remember, we're only reflecting most of the time 2 to 4% of light. And here's showing the tinting aspect of dielectrics versus metals. So looking at these reflections, you'll see on this plastic tube, which is dielectric or a nonmetal, you see the color difference between the original and the reflection is untinted, it's unchanged. So specular reflections on nonmetals tend to be unchanged or desaturated or non-saturated. And then the metals will actually change that color. So you can see that color right here, this white that's coming off here and hitting the metal, is actually turning like a yellow or coppery color due to the metal key. Another concept that we need to understand regarding specular reflections is Fresnel reflectance, or the Fresnel effect. So this is a phenomenon specific to specular reflections where, depending on the angle that we're viewing a surface, it's actually changing how much light is reflected off. So you'll see on this example on the right, looking at this wall, you'll notice that the closer we get to kind of being flush or level with this surface, the more light is actually bouncing off, right? We can see this image much more clearly, but the more you're looking kind of more straight on at the surface, the less light that's actually bouncing off and hitting our eyes. So that image fades away the more we look at it head on. So that, notice again here, look at how clear, or really how intense that reflection is looking based on the angle we're looking at it at. And so the more head-on you view a surface, the less light is reflected back to you as specular. So we call this usually F0, or the reflectance at 0 degrees. So thinking about 0 degrees being looking straight on, and that is going to be the value of how much light is reflected when you're looking at it straight on. The shallower your viewing angle, or a glancing angle that you're looking at the surface, the more light is actually reflected back to you. So a smooth surface that is perfectly perpendicular to our viewing angle, which is described as F90, that'd be a surface that's perfectly perpendicular to the angle we're looking at it at, so essentially turning away from us, will become almost 100% reflective. So you'll look over here on a dielectric material, that F0, or that angle, that the flat straight on angle that we're looking at this surface, is going to have a very low reflectance value, so 2 to 5% on nonmetals. But then if we look at it at a glancing or grazing angle, you can see when we get almost perfectly glancing or grazing or perpendicular to our view, it almost reflects all light. And here's another visualization of that effect. If we look at this lake out here, when we're like kind of looking out across at a glancing angle across the water, you'll notice those reflections are so strong that we can't even see anything underneath the surface. But the more head-on we look at that surface, the less light is reflecting off and hitting our eyes, so we can actually see through the material. And here's one more visualization I want to show. I kind of exaggerated the effect, but here you can see on a shader I set up that the reflections that are facing towards us on the surfaces that are facing towards us are very, very weak, whereas the reflections that as the surface turns away from us are getting much stronger. The next aspect of a material and reflectance that we have to think about is the refractive index, or sometimes called the index of refraction, which represents two different aspects of our material. It describes how light bends when it enters the material, like you'll see with this seal, right? Water has a very, compared to air, high index of refraction. So usually when we see light traveling from air into water, light bends a lot. So that's why it looks like the seal's being decapitated. And it's also describing how much light is bouncing off of the surface. So the higher the index of refraction a material has, the larger the percentage of light is going to be that bounces off the surface. Just as reference, the index of refraction of a vacuum, so not a material or just, an empty space with no material in it, is going to be 1. So that's an empty vacuum. Air is pretty close to a vacuum in terms of how much it's bending light, but it has a very small change in how it bends light. And then water is 1.33, plastic is 1.49, etc. So what's cool is you can look up the real world refractive index for a material, and you can actually accurately calculate how much light is bouncing off of your surface and how much light is bending as it travels through your surface if you were so inclined. So here's a demonstration or diagram of this. So on the top we have air, and on the bottom we have water. So air has an index of refraction of close to 1, and water has an index of refraction close to 1.3. And so you'll see that light, when it comes in, changes direction very, very slightly. So it's actually bending. And due to the difference between these two values, a certain percentage of light is bouncing off. So when two media have different refractive index, light will change direction as it crosses the boundary. And again, it can determine how much light is reflected as a specular. So you'll see in this material shader setup, the higher this index of refraction gets, the more light is actually bouncing off the surface. And something that's interesting is that when the index of refraction of the material is the same as, for instance, air, then you're actually not going to see any light bouncing off. So if two media have the same index of refraction, light will be unaffected by the boundary between the two, so there will be no reflection. So water, for instance, has index of refraction like 1.3, and most materials have an index of refraction that's kind of close. So many objects appear to lose their specular highlights underwater because light isn't bouncing off as it travels from water and enters the surface. So this, cornea is probably going to have an index of refraction like 1.4, 1.35, and that's so close to the index of refraction of water that we're not going to notice any specular reflections. And here we are showing that concept. These index of refraction of this material up here, 1.33, and water, or this material down here, 1.33, that angle is the exact same. So no percentage of light is reflecting off, and all of it's allowed to go into the material. So as a reminder, most dielectric or nonmetal materials reflect only a small amount of light back as specular, usually 2 to 5%. Tip that no real world material will reflect less than 2% of light as reflectance or specular. Metals tend to reflect much more light as specular reflections, so usually 50 to 100% for a polished pure metal. So transparent nonmetals like water, glass, plastic, gemstones, their index of refractions are largely available online because they're easy to measure. But then materials like concrete, fabric, rock, and wood, it's harder to measure those index of refraction. It's some of those materials, it's hard to find the actual index of refraction or reflectance of those materials. Good rules of thumb for the specular range, reflectance range of nonmetals is that no value falls under 2%. Common gemstones actually have really high reflectance, like 5 to 17%. Common liquids fall between 2 to 4%, so that counts as like water, apple juice, orange juice, whatever you want to use. And then if you don't have a reference for that material, how much its reflectance is or its index of refraction is, it's generally a good rule of thumb to use around 4% or 5%, which is about how much light is reflected by plastic, because most nonmetals or dielectrics fall around as reflective as plastic. And so you can look up these charts online. Here's an example of a reflectance chart showing different materials and how much light is reflected and their index of refraction. So remember, index of refraction and how much light is reflected as specular are proportional or related to each other. Another aspect we should keep in mind is that objects that are made from the same material will have the same exact specular value. So that's how much light is being reflected off of the surface is based on the material type. And so if you have two materials that are made of, or two objects that are made of the same material, they should reflect the same exact amount of light from the surface. Surface roughness is what's going to make the reflections look different. So these two, it looks like this one's maybe reflecting more and this one's reflecting less, but that's just due to the roughness spreading out that light. So it's kind of spread out so it looks softer or less intense, but because these are both plastic, they're actually reflecting the same amount of light off of them. So again, if you're looking at a common PBR chart for the reflectance values of nonmetals or dielectrics, you're going to see something like this, right? Most common dielectrics fall between 2 to 5%, and then 4% is like a safe value to use if you don't know how reflective your object is. And then you have an upper bound of 8%, which is common for gemstones. And it's a good idea. These are just linear values, which means that they're just pure number values. It's a good idea to get comfortable with understanding that these pure values, these linear values, correspond to color information if you're plugging it into certain attributes. And so here we can see the difference between a dielectric materials or nonmetals on the left and the metals on the right. So the specular reflections of metals, again, are tinted, so they have a color. And then nonmetals are usually not tinted, so they don't change the color of the reflections. And metals have much stronger reflections. So you can see almost all these metals over here, or materials over here, have very similar values or reflectance values, because again, non-dielectrics fall between a very small range, 2 to 5%. And then metals have very, very bright reflectance values, and they have tinting. The next important concept to understand with physically based rendering is energy conservation. What this says is that the total energy, or thinking of it as light, that is in a system should remain constant. So the incoming light, when we think of it, incoming light interacting with the surface, the amount of light that comes in and the amount of light that travels around and then eventually leaves should be the same or constant. So the light that comes off, though, doesn't necessarily mean that it's going to be the same exact amount of light that comes in, because some light can be absorbed, right? So some portion of light is being fully absorbed and turned into heat. That means we're losing that light. But what this says is that when light comes in and then light leaves, the light that leaves can't be more than light that comes in. Another aspect of energy conservation is that when we think of light coming in and it either reflects off or it goes into the surface, that those two interactions of reflection and diffuse or diffusion are mutually exclusive. What that means is that if I have some portion of light that bounces off, that portion of light also can't enter the surface, right? So if, let's say 2% of my light comes in, I have 100% of light coming in and 2% bounces off, that means 98% of the light, remaining light, is allowed to go into the surface. Or if I have 50% of my light bouncing off, 50% of my light is allowed into the surface. So you can see down here with this diagram that you'll notice we have our reflections, our specular reflections, and our diffuse. So as our reflections or specular get brighter and brighter, you'll notice the diffuse is getting darker and darker because less light is entering the surface. So increasing the microfaceting or the roughness of our reflections means that that light is being spread out across a larger surface. So that reflected light is the same exact amount of light over here and over here that's reflected off the surface, but because it's a rougher surface, that like little sun shape right there is being spread out over a larger a surface area. So if we're thinking about proper energy conservation, that means that those spread out reflections should appear dimmer than the sharp reflections. So they appear dimmer because it's the same amount of light spread out over a larger surface. But again, it's the exact same amount of light that is reflecting off the surface and the exact same amount of light that's entering the surface. It's just the roughness is making it appear like it's dimmer light. So in computer graphics, diffuse is the term we use for that simplification or that grouping of all the light that enters the surface and does all that complex light interactions underneath the surface inside the material. So most materials have very, very shallow light penetration. So we do not have to actually calculate those really expensive or complex light interactions. We use like a simplification in our shader. But that's what diffuse is representing. It's that representing that surface color, light that's not just simply bouncing off the surface. So the key attribute we're going to worry about here is either the diffuse color, or another term you'll hear is albedo. So talking about real world PBR values, coal is one of the darkest naturally occurring materials, and its measured albedo value is 50. So that's not zero, that's not perfectly black. It still has some lightness to it. And then snow, which is one of the brightest non-metal materials in the real world, has 243 as its recorded value out of a maximum of 256. So you'll see it doesn't quite reach white. Even white paper and the whitest material you can think of is still not perfectly white or maximum high brightness value. So our diffuse color or albedo color should fall in the range of 40 to 240 if we're thinking about 0 to 255 as our RGB values. So the color inputs should not factor in lighting information as well. So when we think about our diffuse color or texture map for diffuse or albedo, we shouldn't be thinking about the light and lighting interaction like shadows and highlights, unless you're doing games, which in this case, let's not even consider that. So just keep that in mind as when you're making your texture maps for your albedo or your diffuse material shader parameter, that you don't want lighting information baked into it. And here's some PBR reference charts for our albedo or diffuse color values. So again, most albedo or diffuse colors should fall between 40 and 240. And from if you're thinking about RGB values that go from 0 to 255. And here's some measured real world values for dielectrics. So again, the values are an sRGB, snow 243, coal 50. And I just want to show a few visual examples as reference for what your diffuse color or albedo map might look like for your material. So notice the lighting and shadow and the lighting and shading in the real world interaction with this object, but you'll notice none of that lighting information is in our color map, right? Our color map has no light and shadows, it just has pure material surface color there. And then we have a few more materials here. Again, looking at this sliver here to kind of see the relationship between the object and the color map. So moving on to our specular material settings. One thing I do want to mention here, but we're not going to get into, is that depending on your rendering engine or your shader workflow, your specular reflections are either represented as specular values or with a metallic workflow. But we're not going to get into that. I just do want to mention that depending on your shader and your renderer, that it might be a kind of calculating or describing specular in a different way. But either way, the most important settings we have to worry about is the color or intensity of our specular reflections. So again, remember dielectrics are very, very low and dark, so very little light is being reflected, and it's not tinting our reflections. So in a specular color map, that color for a non-metal is going to be very, very low, and it's not going to be colored at all. And then again, metals reflect a lot more light as specular. So in a specular color map for a metal, the values are going to be very bright and they're going to be tinted or colored. The intensity should be mostly constant across the surface if the material is not changing. So going back to that plastic example I showed earlier with the red chair and the green ball, the reminder that if the material is the exact same across the surface, the brightness or the intensity of our reflections, or how much light is actually reflected off the surface, should remain constant. And then the other setting, of course, we have to worry about is roughness. So that is due to that microfaceting. So the higher our roughness value is in our texture map, the blurrier our reflections are going to appear. So another term you'll see is glossiness, which is the inverse of roughness. So the higher glossiness, the sharper your reflections are. So in certain PBR workflows, microfaceting, which is what caused that specular roughness, is also going to adjust our specular intensity according to that point of the surface. So again, going back to that energy conservation concept, the rougher our specular reflections are, the dimmer our reflections are going to appear to be. Here we can see that concept illustrated on a material in RenderMan. So on the left-hand side, my intensity or color values are black or 0, which means no light is being reflected as specular. And then you'll notice as I increase the value or the brightness of my reflections, that we're almost fully reflecting all light. So all the way at white, we're reflecting all light as specular reflections. So those, as we increase the intensity or brightness of our color, specular color, those reflections get stronger and stronger and stronger. And again, if we change the color of that specular color shader attribute, we can expect our material to then tint the reflections, which is going to make it look metallic. So again, metals are going to have tinted reflections, and then non-metals are going to have non-tinted reflections, and usually really dark specular color values. Specular roughness is going to be probably one of the most important material attributes you're going to have to worry about in your shading workflow, because this is what's going to really add that sense of texture and believability on the surface as light moves across it. So you're seeing in this image right here that all those little shiny imperfections that change across the surface from one area being really shiny and another area being rough is due to specular roughness. And here's another example showing that effect in action. So across the surface, the roughness or the sharpness of our reflections is changing, which makes it look like this one's maybe a little scratched up or maybe a little oily or smudged. And here we can see on a shader I had set up that the lower our value is in the roughness, so 0, the more sharp or shiny our reflections are. And as that roughness value gets closer and higher to 1, then those specular reflections are getting blurrier and blurrier and blurrier. And again, going back to something I mentioned earlier, glossiness and roughness are the inverse of each other. So if you have a glossiness attribute, shader attribute instead of roughness, then if the value is 0 in the glossiness, that means it's really rough. But the higher that value is in the glossiness, aka the more glossy it is, the shinier our reflections are. So going from, again, that terminology, glossy is shiny reflections, and then rough is really blurry reflections. And because I like showing so many examples, here's just a few more visual examples showing the difference between glossiness and roughness. So here we're increasing the glossiness from very low value to a high value. And here it is again on a metal. Here's a shader where we're actually animating that roughness attribute, so making it more and more rough. And you can see by adding breakup or a texture map to our roughness, so adding variation to our roughness, we can make something look very believable or realistic compared to if we don't vary our roughness. So here on the left-hand side top, you can see these grapes have a constant roughness. So the surface looks really, really clean, which makes it look really fake. So almost everything in real life has some imperfections and breakup across the surface and variation across that breakup. So you'll see when they add this texture map that changes whether it's shiny or rough as it travels across the surface, that looks way more believable. And even on perfect objects like this phone, adding some kind of roughness or breakup like smudges and scratches and cracks is just going to make the object look more realistic or believable. And so here's just another example showing with no roughness, so it's just constant, or no roughness texture map, so it still has a roughness attribute, but we're then actually plugging in a texture map to vary that roughness. And going back to that idea of energy conservation, both of these materials have the same percentage of light that is specular or bouncing off the surface and being reflected. But the difference is how rough or glossy they are. So that water is very, very glossy, so very perfect reflections. And then that mud is very imperfect reflection, so a very rough surface. So again, it looks like the water is reflecting more light, but in reality, that light is just concentrated on a smaller surface, whereas on a rougher surface, that same amount of light is being spread out across the surface and heading in a lot of different directions. Not all of it's reaching my eyes. And applying our physically based rendering concepts to that specular color or how much light is being reflected, that general rule of thumb is that the specular intensity or how much light is reflected off of a surface does not change across the surface. So instead, when we use texture maps, most of the time we're just varying how rough our reflections are, not how much light's bouncing off. However, the specular value, how much light is reflected off the surface, will change or vary if the surface actually changes material properties. So a metal that turns into a dielectric due to rust or corrosion or dirt or mud will actually change how much light it's reflecting off because it's actually changing its material chemical compound. So all this pure metal here is going to reflect the same amount of light, and all this dirt and rust material is going to reflect the same amount of light. But when it changes from metal to that rust or that dirt, it's changing how much light is being reflected. They don't have the same reflectance. So, very long video, but in summary, the diffuse is the surface color of our nonmetals. So that's the term we use for this, describing that broad reflectance or that broad light interaction of light entering the surface, scattering and coming back out, and what we see as color. Our diffuse colors for PBR materials lies between 40 to 240 if you're using sRGB color values from 0 to 255. Specular is describing those highlights, or the light that doesn't enter the surface but bounces off. So that's how reflective our material is. The amount of light that's being reflected, or the intensity of our specular, is based on the material type, whether it's plastic or wood or stone or metal. And then our specular roughness is how sharp or blurry our reflections are. And comparing dielectrics to metals, dielectrics have a diffuse color, so it has a diffuse component. The specular is grayscale, so it's not tinting the reflections. And the amount of light that's being reflected is very low. Usually, most commonly, 2 to 5% of light is being reflected off. And then metals, compared to dielectrics, have no diffuse component, so it's all specular. The specular reflections are tinted, so it's actually changing the color of our reflections, except for in this case, it's like aluminum or steel, which usually barely tints the metal or the reflections. And then the amount of light that's reflected is pretty high, between 50 to 100%.